So now we're going to embark on a journey into Liouville space. And Liouville space is a linear vector space, just like Hilbert space. The only difference is it's where we consider the density to be a vector. All right, so let's figure out some notation and some sort of observations and properties. Let's take the density operator, which is now we're going to be thinking of as our, sort of primordial thing. And as we have discussed numerous times, sometimes you can make progress in quantum mechanics by simply inserting the identity in various locations. That's what we're going to do here. So we're going to assume every time I insert the identity, as a sum over outer products for projectors onto basis vectors, we're assuming that it's a typical, complete orthonormal basis. So, for example, I can express it like this with J's. And if you don't like this abstract idea, that's fine. Just think of it like the eigenvectors of some Hamiltonian, right? Because that'll be in the Hilbert space or the Liouville space of whatever operator you're interested in, right? And so it's those eigenvectors or another operator, right? And if you want to think of it in terms of Cartesian coordinates, you can just imagine that we have an infinite dimension of those if we need them. All right, this is one sort of insertion of I, and the other one is going to go over here. We can use the K. All right, and it sort of seems like, nothing's happened, but let's see what happens here. What we're going to do is we're going to bring them all together. So we have a sum on J and K. We're going to have J out front. Then we see J rho K. Well, that's the JK element of rho. That's the JK matrix element of rho. Okay. Okay. So this is, I can just move this row wherever I like. And what I notice is that I can rewrite the density operator as a superposition of density operators, essentially, right? These are not projectors unless J and K are equal to each other, but they are like operators. Sorry, of course they're operators, but they're like density operators. So what's the analogy here? The analogy here is that if I had a state vector, psi, I could express the state vector in a basis by inserting I here, right? And then I would have the sum on, let's call it J, whatever J is. And this we would usually refer to as something like C sub J, the coefficient or the component of psi that's along the J direction. Right? In other words, it's a linear superposition of basis vectors. What do we would have for the density operator? We have a linear superposition of these operators. Okay? So the analogy is direct. That's what I mean. That's what I want to say here. It's direct. It's so direct that you can think of these as the unit vectors or unit operators, if you will, that we will use for Liouville space. So we're going to make a new notation for an operator of this form. We're going to call it this. So this whole thing here is going to be called JK with two arrowheads. Right? So this equation, which now is simply transformed by notation alone, two arrowheads. We do this to make the direct analogy or isomorphism between the density operator version and the state vector or any vector representation in Hilbert space. Why do we adopt this Dirac-like notation? Well, because it turns out if you treat this and follow the rules that way you did in Hilbert space, almost all the time, exactly the same thing will happen. Here's an example. What if we do the adjoint of JK? Well, we know what that's going to be. That's going to be KJ. So look at this. If this was JK with 2, well, what's the adjoint of that? It's the other way around. All right. So we're going to call that this. Okay, so if you want to switch back and forth between this sort of Liouville space notation and the Hilbert space notation, when you see JK or a pair of 2 indices, you will put these. But if you see the arrow pointing to the right, you swap the order. Okay, so why is that useful? First of all, there was no reason I had to pick the density operator here. Could have been any operator. So that means, of course, if I put an I here and an I here for A, I'm going to have exactly the same thing. So I'm just going to cut to the chase here. We're going to have A, JK, JK. Right? So what we're doing is we write the operator A in the basis JK, the same basis, but two different like replications of it. Okay. What about the adjoint of a matrix or adjoint of an operator? Switching it around, if I have a B, for example, then I can have B dagger. Oops. Sorry. So we see this is the operator A, right? We've written the operator A as a coefficient, and then if we insist on still thinking of this in Hilbert space, this will be an operator. But in our new space, this is going to be a vector. All right? So the Hilbert space operator becomes a Liouville space vector. I can do the same thing with B. And I could have done it with A as well, of course, right? So B would be like, right, JK, BJK, JK. But we know in Hilbert space we have adjoints of operators. Not every single operator is Hermitian. Right, so if we want B dagger, then of course we should have something like the dagger of this. And this will be, let's do the whole thing. All right, and then we literally just follow our rules. So we still have the sum, that doesn't change. This is a potentially complex number, so we should make it the complex conjugate, BJK star. And then we switch the bra, or the ket, to a bra type vector. Okay, so we have a way of making adjoints of operators, which become bra Liouville space vectors. All right. Now let's ask the question, what about a scalar product of two Liouville space vectors? All right, so I'll pick A and B. Well, I want to calculate their scalar product. Remember, scalar product is one of the key components that you have to have in a linear space. So I can just write this down based on what we've just done. So we have the sum on JK, B, JK star. Notice I'm not just switching it to JK, KJ, because I'm not assuming that this is a Hermitian. We have that times the A1, and we have to be careful about our notation. This is really a bunch of sums, so we have to separate them all out, or keep track of them all. So I have to use two new indices here, ALM and LM. All right, which you can then combine all the sums together. So JK, LM, I'll have the numbers, BJK star ALM. And then what do we have? JK LM. Okay, now, what is this? you can probably guess right away that this is going to be delta function related because these are all the same basis. It makes no sense to take combinations of different basis vectors. That would make no sense. I mean, it's not no sense. It's just not convenient. All right, so here is the way to think about this quickly is that we're going to have pairs of these things, right? JK. So when we see JK written this way, what does that mean? JK written this way is actually equal to KJ. Whoops. KJ. We're kind of like exploding this up, right? And then this one's just LM. So what does that tell us here? It tells us that we have the J and the L will give us delta JL. Okay, by expanding this out, what we notice is that we do get one thing of delta. What we expect to see is that this should look something like the delta of JKLM. It should be something like these two should be the same because we expect them, if they're going to act like basis vectors in Liouville space, they should act like basis vectors in Hilbert space as well. What's the problem? The problem is, although I do get one delta function here, I'm left over with an operator here, the Km operator. So how do we get ourselves around that? We add new math, essentially, a definition, which is to say that when you see a scalar product like this, okay, what we need to do is we can calculate through to here, but we need to actually calculate the trace of this whole thing, right? So this is not quite it, right? So we need to put in here trace. And when we do that, you'll see in a minute that that solves this problem. So what does trace of this do? It's a lot to write again, so I'm not going to write it again. What it does is it says we pick two, vectors that are the same. So let's just call them like alpha, for example. So this is going to be the sum on alpha. We already got rid of the J and L sums because they have to be equal to each other. So J is equal to L. So we'll just have one value of either J or L, right? Or we can leave the delta function in there. So we have the sum on alpha, which is coming from the trace, B, J, K star, ALM. Okay, and then we have K, M, alpha, and delta JL. All right, so notice what happens. This is just a number, so I can move it. All right, then if we go back up to here, what do we have? We have the sum on alpha. So alpha is going to take alpha and kappa, alpha and k, make them equal to each other. So that's going to be a delta alpha k. And this is going to be a delta m alpha. So if k is equal to alpha and m is also equal to alpha, then we know that k has to be equal to m. All right, so that's going to give us then, there's still the sum, which I left out. All right, let's just put the sum numbers down here. So jklm. All right, so now what we know happens is that we get rid of the L and M terms because we have a new delta, right? So we're going to have, we can write it all out like this. We're only going to be doing this once. BJK star, oops, ALM. All right, and then we have delta JL, delta KM. All right, so if J is equal to L and K is equal to M, then we don't need the LM term. We also don't need the alpha. There's no alpha sum anymore. We got rid of that at the beginning. So this all ends up being then a sum on J and K, BJK star ALM. There's no LM. Right, so L is J and M is K. Okay, so we're going to check and see what happens if we just use basis vectors and consider the scalar product of those two, just to get our clear. We would, before, of course, we weren't doing basis vectors, we were doing any arbitrary vectors. So if we do basis vectors, we get something like this. So if I picked jk and then let's say mn, remember now with our definition, we're going to do the trace of this where we blow it, we explode it out. So jk on the left, pointing to the left, is kj. And on the right, we have just mn. Right? We already got that this is delta jm, just like on the previous one. And then when we do the trace, we're going to sum over the diagonal elements of what's left over. Diagonal elements will be like alpha k and alpha. So I'll just write that out so we can see, so people see all the terms. Sometimes this can fly by a little fast. So we have alpha k n alpha delta jm from before. Right? And so what does this give us? This gives us delta alpha k, delta n alpha, which is the equivalent to delta kn. Right? So what you end up with after all of this is probably what you expected. You get delta kn, so that's kn, the second element, and delta jm, the first element. So those two things have to be the same for this to be not zero. And that's what we mean by orthonormal basis in Liouville space. Okay, so what are some other things that you can do with these sort of definitions? One of them is you can figure out what the matrix elements of a Hilbert space operator are. For example, if we have the operator A in Hilbert space, right, we now understand that we can represent that as a vector in Liouville space. And if we want to ask something that you'll want to know a lot of times in Hilbert space are like the matrix elements. So let's calculate, or let's evaluate jk A and see what that is. Okay, so we'll just follow the rules. This is trace kj A. Okay. Now, what do we do here? We take the, we're going to have AJ, and then the trace means we're adding over the diagonal elements so that we can do the same kind of thing, like sum over, let's say, alpha as a sort of dummy index. We put alpha here and here. Right, then we would have k alpha, delta k alpha, which just tells us that k is equal to alpha. So then when we see the alpha over here, we'll have j a alpha, but we know that that means j a k. So this term is equal to j a k, which is just a jk, the jk element of A. Right? So when you do this scalar product of the Hilbert space operator, but now a Liouville space vector, with a unit vector in Liouville space, you get a matrix element of the Hilbert space operator. Right? Another way of thinking about that, which is probably the more correct way, is that A is really a vector, and this is giving us the scalar product with the jk basis vector, just like it would up here. Right? So if we imagine putting it into a finite basis, we would have like A11, A12, A13, and so on. And taking the jk, the 1, 3 element of this, just pulls out, for example, that term from our vector. All right, there's going to be even more things that you can do that are completely analogous with Hilbert space that we'll list now. Okay, so this next derivation is a kind of a clever little sleight of hand. If we start with A, like we did, we can write this in a basis, right? Okay, by inserting in the Hilbert space viewpoint, right? Inserting that 1 in both sides, and then recognizing that we can sum over that. So we'll have the sum over j and k of A, jk, jk, right? We're writing this operator, which is a vector in Liouville space, in a basis. Now, This is a number, right? So Tetris style, it can slide. So let's do that. Oops. Okay. Now, what did we just find out about the matrix elements of Kj, or the components Jk, sorry, Ajk? We figured out we can write them like this. So let's do that. Cannot fit everything. So we're just going to write this thing here and put it up here. Well, that's interesting. What did we get? We got that A is equal to A. Right? This is the Liouville space A. So what does that mean about this? Yeah, like you might have expected, this is equal to 1. So this is the so-called closure relationship. I actually don't know why they use that term in math. We also have used this when we inserted the identity. So if you insert the identity, it's the same thing as essentially multiplying by 1. We called this the spectral resolution of the identity because we were displaying the identity in one of the eigenbases of some operator. So the same thing's happening here. So you get a couple ideas. First of all, that suggests that these are projection operators, which you can prove that they are. Do it again, twice, do it twice, and you'll get the same result. As long as you remember how to calculate a scalar product, it's not the same as in Hilbert space. We have to add one new operation, which is do what you thought you would have to do and then take the trace. Okay, so we have a way now of writing the identity, taking the scalar product. Obviously, we can add and subtract, we can multiply by a constant. So when you work out, we've basically done all the conditions for a linear space with these vectors that we have here. Right? So Liouville space is a linear space. And we might ask, we've worked out how to write vectors in Liouville space. That's math. Our science is that we're going to take operators from Hilbert space and represent them as vectors in Liouville space. The one that we've thought of so far is the density operator. So the question is, what is an operator in Liouville space? What are they? What are they? So that's what we're going to figure out. Okay, so we need to think about how to actually write down an operator. So an operator is something, of course, that's going to operate on a vector and return another vector. Right? That's sort of one way of thinking about what an operator is. So let's call the operator, for example, F. And sometimes people use curly letters to indicate Liouville space operators. I will try my best to stick to that notation. If you look at the Mukamel book, this is how they do it. All right. So what we're going to do, just like in Hilbert space, we had an operator, we put I and I. Now we know how to do I. So let's see what happens when we put I here and I here. All right. So not much is different, right? We just have to have 4 indices. We'll do JK, MN. Right? We put in the identity, so that's going to be JK, 2 arrows, JK, F, and then MN, MN. Okay, and then all that happens is we see our operator here has 4 indices. So to reference a location in the matrix that we will represent this operator in, we'll have F, JK, MN. Right, so that's how we write this down. JK, MN, F, JK, MN, And then what's left over is the vectors. J, K, M, N. Right, so this would be a matrix if you evaluated it and put numbers in. And then this is the vector stuff that's left in Liouville space. Okay. So what you're going to see that we can do is that we can actually rewrite the Liouville equation in Liouville space, right? And that's going to be next.